Okay, so ladies and gentlemen, everybody in the room and also connected online, it is my real pleasure to be here on this occasion, on this important occasion, to present what we achieved in the project team number 2, whose title or whose name was exactly the same as my presentation. So, New Items in Fire Design of Concrete Structures. A very simple title, but still paved the way for a lot of work. Okay, briefly, the table of contents of my presentation, the overview is very short, and then we'll go through some modifications, some significant modifications which we made in the previous version of the Eurocode for the new draft that you now have available. Clearly, because of time restraints, I cannot go into details of everything. I would like to just point out the basics and the most important things, being aware of the fact that in the publication of Hormigón y Acero, you have a paper which describes in more detail some aspects. Just the quick overview is to show you what the project team was, because also this presentation was prepared in cooperation with my colleagues, left to right, Tom Lennon from BRE, Jochen Seefus from Braunschweig University, the head of the project team, which is Fabienne Robert from CERIB, myself, to the far right is Patrick Bischoff from ETH Zurich, and there you can see not so far right Hans Gans, who performed a wise supervision of our work together with Michael Hallgren, who is not in the picture. I think it was a meeting in Rome. Yes, probably there is some carbonara left in Fabienne's plate. Big portions in Rome, kind of clearly. So coming to the details of my presentation, for clause 4, the basis of design, we try to stick to the philosophy of the levels of approximation. So basically, we have typically 4 levels in fire design. The most well-known, the most simple is the tabulated design data. We like it when we have to perform some design, some quick design, some pre-design of the structures. But then again, it is quite limiting because you have to stick to dimensions and prescriptions as regarding, for example, the gross concrete cover, which is one of the main driving parameters as regards fire resistance. Then we have simplified design methods, which are very useful when you perform some cross-sectional resistance. Now, this required a lot of work because clearly in fire, there are certain aspects that cannot be limited on the sole cross-sectional resistance. I should mention the fact that, for example, in fire resistance, you have a lot of papers and a lot of tests devoted to columns. Now, that's because of buckling problems. And buckling problems, when you deal with reinforced concrete, you know, is something that is not so significant in ambient conditions, with the exception, of course, of, for example, the high columns you find in industrial facilities. In fire, the effects of the damage and of the stiffness reduction can pave the ways to unexpected buckling failures, and that's why we had to do a lot of work on columns, and you will see some examples later on. Then we have, of course, advanced design methods, so finite elements method. Not much was done about this. And then, of course, tests, but this was not the specific object of the standard we worked on. And clearly, we choose an appropriate level of approximation depending on the amount of information and the required accuracy of the design. Clearly, we still are within the domain of the classic approach based on the standard fire, which is the ISO 834 fire curve. So tabulated design data, simplified design methods, and also the rules for explosive spalling are primarily based on this ISO 834 fire. I should mention this because the new frontier, but this is probably the next Eurocode, is to work on natural fires, which are fires which are significantly different from the ISO 834 fire, since they have also the cooling phase, and the cooling phase requires a lot of attention because of what happens inside the material, and also because the thermal analysis is a little bit more complex. So let's go to clause 5, dealing with material properties. Here are the main changes. We have now a unique conductivity curve for normal weight concrete and high strength concrete at elevated temperatures, and this is a big plus. Then we have a high strength concrete reduction factor, which is now only 1. Previously, we had 3 classes. We have provisions as regards the aspects I was just mentioning. So what happens to concrete strength when you consider the descending temperature branch? So you clearly lose strength when you go up with temperature. What happens when you cool concrete down? Does it recover? Doesn't it recover? So we try to answer this. And then there are some additional provisions and some simplifications regarding steel strength decay and the strength and deformation properties for pre-stressing steel. We also have 3 new annexes, one of which is normative, and it deals with lightweight aggregate concrete. And then we have 2 informative annexes dealing with 2 types of concrete, which are becoming more and more popular these days. So fiber reinforced concrete and recycled aggregates concrete. As regards the conductivity, this is a big and important improvement because we move from the previous 2 curves. You see the gray one, the dark gray one, the so-called upper curve, and the light gray one, which was simply called the lower curve. And if I may seem a little bit too generic as regards the names of these curves, it's because there was never really quite some indication about when to use one curve and when to use the other. For example, somebody argued, you know, plots are very popular these days. Everything that happens in the world can be explained by means of plots, okay? Somebody said concrete behaves like the lower curve, so it has a very strong insulating power. But some people didn't like that, because if concrete is so good at insulating, it may outperform other structural materials. So let's also put a higher curve. That's something I heard. Somebody said, okay, the lower curve is for siliceous, the higher curve is for calcareous, or the other way around. But no clear indication was given. So we switched to one unique curve, which was calibrated on the basis of several design data. It used to be in the National Annex of France. The fact that it's not a closed form curve, so it's not a unique equation from the beginning to the end, is not a big problem, because this curve is typically used for numerical analysis. And you know, when you do numerical analysis, it makes no difference to have single values or to have a closed form expression. You have to input points anyway. As regards high strength concrete reduction factor, there you can see the old 3 classes, black, dark gray, and light gray. And now we only have the new, which is red and dashed. Clearly, this is a big simplification, also because I should say that when it comes to the fire behavior, it is important to accurately represent the temperature distribution. It is important to take into the account the decay of compressive strength, but I still have to find problems where the decay of concrete compressive strength is a decisive factor, okay? So this is what we did. It greatly simplifies the provisions. It is, of course, well motivated, but I should say, if I was to stress the importance, I would rather focus on conductivity rather than on compressive strength, okay? As regards concrete strength in the cooling phase, this was a big issue because we previously had provisions as regards the cooling phase in the Eurocode 4 fire part. We didn't have any in the Eurocode 2 fire part. And this was a big difference and something which is quite strange. So apparently, Eurocode 4, which was devoted to composite structures, had more information than the specific standard devoted to concrete structures. What did we do? We simply included those provisions, clearly after some checking about experimental data, which are still scanty nowadays. So knowing what happens in the hot stage is easy. Knowing what happens when the concrete has cooled down is easy. Knowing what happens in between the hot state and the residual state is still a source of debate. We have some tests carried out at ETHZ some years ago. I personally did some tests recently within an ACI project, but still we don't have many information. I think this is a big challenge for the Eurocode to come, to clearly give an indication about what happens in the cooling phase. And not only as regards compressive strength, also as regards conductivity, okay? I showed you the curves previously. You heat up, the conductivity goes down. What if you cool down? Does it go back along a horizontal line? Does it go back the same way? Reversibility versus irreversibility, a big problem from both the practical point of view and the theoretical point of view, because you then have to explain why the behavior is irreversible, if it is. What about tabulated design data? Well, we still focus on concretes of usual density, thereby meaning between 2,000 and 2,600 kilograms per cubic meter. For concretes with higher strength, high compressive strength, the tabulated data have a limit, so they should not be used for fire resistance larger than 120 minutes. There is a risk of severe spalling if the limitation rules to avoid spalling are not complied with, but I will go back to this later. Then there are certain other prescriptions. So these are the main changes, but the most important thing is that, for example, we took into account and we gave more emphasis to eliminating the differences between what we had previously. So we had method A and method B. And as far as I could learn from my experience with research in the fire domain, the only difference is that one is called A and the other is called B. Okay, there were also some differences in input parameters, but I couldn't get the difference between the two methods. So we tried to make that simple. So basically we had everything based on this degree of utilization, which means how much the column is stressed in fire conditions, this mu Fi, and then this method, which was retained, can still be applied where the buckling length is in fire is half of the buckling length at ambient conditions. And then we try to extend the method by giving some provisions when you cannot make sure that the buckling length in fire is half of the buckling length in ambient conditions. For example, there are some provisions which require to calculate this degree of utilization, still mu Fi with an apex, and with a modified effective length, which is L0 equal to twice the buckling length in fire. So no major details. I just want to stress the fact that more attention was given to the specific boundary conditions, which can significantly different from what happens in ambient conditions, because clearly in fire you have hot areas and cold areas. And the cold areas, they retain their stiffness, whereas the hot members, they lose their stiffness. So since there is no absolute level of restraint, it's always a matter of relative level of restraint. The restraint and therefore the buckling length may significantly change and be affected by fire. Here, some examples. Previously, for columns exposed on one side, we just had that column to the left, where it was basically only the highest load level, so mu Fi 07, which means column is stressed to the highest level it can be stressed in fire conditions. All coefficients, loads, and materials taken into account. Now we have a more specific indication and inclusion of the load level, which is a parameter in design. I mean, not all the columns are stressed to their maximum level. I was talking during the break. That's my experience in Italy. When you design columns in seismic areas, you have to keep the actual force low because of ductility requirements. And having the load level low is another means for guaranteeing a higher fire resistance, clearly. So why not take it into account? This was an example. Together with the columns, there were more tables added concerning load-bearing walls. I can assure you that this is a big topic also in my country. There were never clear-cut provisions as regards load-bearing walls. So this comes as a sure plus. And then clause 7 for the simplified methods. Again, I should stress a big leap forward is in the fact that we clearly worked on simplified design methods for cross-sectional resistance. And we gave some additional provisions as regards advanced design methods. But here you can see a temperature map. That's because a significant effort was devoted to making the provisions for the thermal analysis more simple. And I will show you why. So thermal analysis is one item, and then there is always the mechanical analysis. The two concepts go together in fire conditions. And here the basic principle is this. And if I was to summarize everything in simple indications, when you have the fire effect, and you can see there is an FSD Fi. So the force in the steel as a function of time is the product of the area of steel times the yield strength of steel. And there is in the middle a coefficient which takes into account the effect of fire through the temperature theta. Now, you can either put the coefficient to the yield strength, in which case you are more tied to what happens physically, so the yield strength going down, or you can put the K coefficient to the area of steel, thereby reducing the geometry. And this is our approach. So you will find in the paper that all these simplified methods, which are clearly based on the effects of fire, which is reducing the strength of the materials, are sometimes translated into a more intuitive concept, which is the reduction of geometry. Because when we think about fire, and specifically when we think about material which burn, wood, for example, we are used to think about fire as a consumption of material. Clearly, concrete does not burn, steel does not burn, they lose strength, but you can make an assumption which is similar. So that's why you find some indications in the paper as regards the reduced section. This is the concept, but the mechanical principle is always that, okay? You lose strength, but as regards the calculation, it doesn't matter whether you put the coefficient K on the geometry or on the strength. It's the same. And then here, verification in the very simple case of bending. I was mentioning thermal analysis. So one big effort was devoted to getting rid of the temperature profiles we had in the Annex A. So basically what you had in the previous Eurocode was thermal analysis performed graphically. This is surely very straightforward. It's a little bit complicated and also not so flexible. Now we have closed form expressions which cover members exposed on one side, member exposed on two sides, member exposed on four sides, and I should mention also the case of member exposed on three sides. There was a lot of work done also, I should say, in the task group before we started with our work in a project team to validate these provisions. I myself use them for academic purposes. The expressions may seem complicated, so you may suffer a little bit in the beginning when you have to implement this into spreadsheets, but then they are truly flexible, okay? Truly flexible, and they basically allow you to get rid of a thermal analysis by means of finite elements method, which you can still do if you prefer, but this is a very simple tool and surely easier to handle than temperature profiles, where you have to put the bars, look at the positions of the isotherms, okay? That's, in my opinion, it's a big leap forward. As regards the simplified design methods, I cannot go into the details, so I would just like to stress the fact that this is the situation we had in the old version of the Eurocode. You can see how many methods we had for designing. Now, I should say, in my experience, there were certain methods which were popular. For example, the 500 degrees centigrade isotherm method is a very popular method. All the designers like it. because of its simplicity. Now, we may be criticized about this, but we got rid of this method. And not because it didn't work, or not only because it didn't work in certain cases. It's because we made it simpler. We provided a method which is even simpler than the 500 degrees centigrade isotherm method. We didn't invent anything. The method was there before, but it was in an annex of the Eurocode. We simply brought it in the main body. In the case of bending and axial load, we clearly understood as time went on that the method didn't work for columns, especially in the case of a significant effect of the axial load. So the problem I was mentioning before, when you are at risk of buckling, you cannot simply go into the cross-section and look at what happens in terms of compression force and tension force. Things are quite more complicated. So what happened is we got rid of this method here, and then this other method here. I should mention that if you look into the details, we now have a refined zone method for columns with significant axial loads. Again, the consideration is the same as with the thermal analysis. You may suffer a little bit at the beginning. There are certain things which you have to understand, but then the application is definitely more straightforward and accurate than what we had previously. Again, on detailing, this was, I mean, the provisions we had in the Eurocode were okay on the whole. The thing we tried to do within the project team was to give them further validations. As we realized as the process went on, these provisions mainly came from good practice indications by which originated from several tests carried out at Braunschweig, which is, as regards fire, a little bit the capital of European universities. Everything was done very well and in an accurate way in Braunschweig in the past. So our effort was simply to validate further the good practice rules which were given. And so a lot of work was done on looking at continuous labs, which undergo that significant effect, which you see in the graph at the top left of my slide. So there is a big moment redistribution. So basically, when you have a continuous beam, it tends to behave as if it was two cantilevers, one in face of each other. Clearly, this requires a lot of ductility. You also have to be careful about how you detail the reinforcement. Otherwise, you get a sudden failure because there is not enough bending capacity. So several numerical simulation, cross-examination of the experimental work done specifically in Braunschweig. We also have a paper published in Structural Concrete together with a colleague from ETH. And this is basically the new provisions we have. So some update and some confirmation of older rules. And then I should end my presentation. How much time is left, Chairman, Mr. Chairman? How much? Oh, I was too fast, so I should speak slowly. Okay. No, actually, I came to Spaulding, and the Spaulding previously had some indications. Now we have some more indications. There were some significant changes which were brought in by the work in the project team. So now everything that deals with Spaulding is in a new clause, which is called, clause number 10. There was a big decision which relates to the moisture content. There was previously an indication as regards the moisture content where the Spaulding risk was high or where the Spaulding risk was low. These data were not so clearly verified. And so the indication of the moisture content threshold was deleted. For a specific class of structures, the structures where the resistance required is only 15 minutes, no spalling verification is required. Basically, that's because based on the evidence, there are no significant spalling phenomena in the first minutes of a fire, and then we added some new rules. Here you see an overview of the rules for spalling. So what I was mentioning before, for R15, verification of spalling may be omitted except for a clause, which I'll show later. Then there are structures in a water-saturated environment or insulating permanent formwork, which prevents concrete from drying. So in a certain sense, no clear indication as regards moisture content is given, but these are clearly structures where water plays a role. So there should be a specific assessment of spalling undertaken, or polypropylene fibers should be specified. That's because when you have no further indications, using polypropylene fibers always proves to be a means to prevent spalling. And then basically the big innovation was the fact that we tried to simplify again the provisions. This was one of our polar stars during the work in the project team, to make things simpler. Okay, so there is a threshold as regarding strength with this key value, which is 70 megapascals. And another factor which proved to be decisive in determining the spalling is the presence of silica fume. Now, concretes with high contents of silica fume prove to be very, very spalling sensitive. In this case, there is some indication, and the last provision is with this and silica fume content larger than a certain threshold, or the strength larger than 70 megapascals. In this case, again, specific assessment of spalling should be undertaken, or polypropylene fibers should be specified as per the clauses which are listed there. Here, there is a sort of explanation on how this works. For example, when you are with R15, verification of spalling may be omitted except for clause 10.2. And this is specifically indicated. You should not omit the spalling verification if you have members with webs thinner than 80 millimeters. This, in my experience, was one of the few cases, or there are several cases, where spalling had a dire consequence on the structural bearing capacity of a concrete member. I will show you some picture later on, but if you think about the pre-stressed eye girders you have, for example, in industrial facilities with very thin webs, there a spalling of the web may significantly and adversely affect the shear behavior and the shear bearing capacity. So that's why this requirement was introduced. And then this specific clause, verification of spalling may be omitted except for clause number 5. So the case of isolated members with 3 sides exposed, whose dimensions do not comply with table 10.2. And here again, as you see, the table 10.2 is related to the minimum web thickness of isolated members, which have to be regarded with specific attention. So if I was to give you a clear-cut information about everything that deals with spalling, we made the rules simpler, I think. Some arbitrary parameters have been eliminated. Specific attention should be devoted whenever you are faced to thin members, which is typically the case with precast elements. I should say elements and not members. That I learned during the work in the project team. Okay. When it's precast or prefabricated, it's an element. Okay, then here again some indications. Loss of strength may be assessed using a reduced effective cross-section where the spalled layer of concrete is omitted when calculating the strength. This is a typical design approach. If you don't know what to do with spalling, you simply take it into account as a further reduction of section. For example, in big infrastructures, typically we work on fire scenarios, and to each fire scenario, there is a corresponding spalling level, which should come from some experimental data. Either you do the tests yourself or you get from them from the literature. And this is a very straightforward approach. You take spalling into account as a reduction of section. Now, point 9, I should mention, when assessment based on experimental evidence is required, it should be obtained from tests representative of the conditions of the structural member in terms of geometry, stress, and moisture content. This is a sentence which is very clear. Clearly, it paves the way to different possible test methodologies as regards spalling. To my knowledge, there is still no general consensus on what the best spalling test is. There are certain proposals. I have a colleague in Milan who is who is a big expert in spalling. He's now running a PhD thesis on the topic. It's a complex problem, also because we recently had some evidence of behaviors which are not what you typically expect when you have spalling. I mean, spalling is always like the explosion of concrete chips from the surface, okay? What we had in Milano is specimens, bulky specimens heated up in the furnace, exploding literally, breaking apart the whole furnace, really something which was not expected, and needless to say, with high performance concrete. So I just want to tell you the problem of spalling as regards its interpretation and also the performance of tests is still under debate because it seems to be a very complex problem. At certain times, experts do not even agree whether some explosion-like phenomenon is spalling or not, okay? And then here you have a provision which is always something which everybody knows. When you don't know what to do, adding polypropylene fibers is a good means to mitigate spalling. Here, a minimum content is given equal to 50, a minimum content KPP with, and provisions are given as regards the diameter. And then there is a value of KPP, which is 2 kilograms per cubic meter. But here we could not get rid of the national annex. We tried as much as possible to get rid of national determined parameters. In this case, evidence was still quite mixed. So we felt it wise to retain this, this liberty, this freedom to decide. Again, no general model on spalling. This is why I'm showing these tables, which were sent to me by Fabienne. She wanted to point out that even if the spalling clause still retains a nature which is somewhat prescriptive, it's because we can't do any better. And what we could do is to base the considerations on a lot of data. And I think that's the good approach. And it's probably something that was missing in the previous version of the Eurocode, where we could not always trace back the provisions to well-documented tests. So I go back to what Hans was saying this morning. We try to work on mechanical models to motivate everything whenever we can. If we cannot, then everything should be based on well-documented tests. And this is the philosophy of the new provisions and their validation. Finally, just to tell you, this was the phenomenon I was mentioning before. There to the left, you see what happens in thin webs when you have spalling. Basically, you lose everything that's between the top flange and the bottom flange. And this is a problem. We had a failure of such a beam in Italy. And unfortunately, one firefighter was killed. So imagine, it's a problem of safety of people in the end. How much? This is just to say that, again, here, this is the sentence which points out to the fact that depending on whether you have reinforcement in one direction or in the two direction, there might be a different behavior. But the core is providing minimum web dimensions and then to allow for more than one vertical layer of reinforcement is a means of providing a more robust design. And more robust design is typically avoiding that what you see on the left happens, because it may have dire consequences. And well before 2 minutes, I'm done with it. Thank you, everybody.